In this lesson, we're going to begin the first introduction to this broad topic that spans the entire course, which is functions. It's in the name of the course. It's obviously something very important, and it's something that we're going to be dealing with quite repeatedly. I'm going to start with something that should be very familiar to you, which is the idea of a table of values. For many of the concepts, the first time that you are exposed to them, your first experience with them, has to do with a table of values. When you first learn graphing, you construct a table of values, and every time we introduce some sort of new relation, you start with a straight line, you do a table of values, you draw it. You learn about quadratics and parabolas, you do a table of values and you draw it. Now, we're going to be using this in a slightly different way, not to illustrate using a drawing, but that process of creating a table of values actually lines up quite nicely with the idea of functions and function notation. So when we create a table of values, we normally start off with some values, or we create some values for the independent variable, which in this case I'm just labeling as x. That's our generic independent variable. And if we had a linear relation, our dependent variable would be given the equation of some sort of straight line. So I've just made up an equation in the form y equals mx plus b. And so our dependent variable is y, and our dependent variable is defined in terms of this set of rules, 2x minus 3. So when I put in a value of x equals 1, my y value is 2 times 1 minus 3, which of course is just going to give me 4 minus 3, 2 minus 3 is negative 1. And then I put in an x value of 2, so that's going to be 2 times x, which becomes 2 times 2 minus 3. And this one, I was jumping ahead there, 4 minus 3 is equal to positive 1. And then when I put in my input value of 3, I get 2 times 3 minus 3. And that's going to be 6 minus 3, which is going to give me 3. So for my independent variable, when I put in an independent variable value of 1, I got out a dependent value of negative 1. Input of 2 gave me an output of 1. Input of 3 gave me an output of 3. With a quadratic relation, we would do the exact same kind of process. It's still the idea of setting values or assigning values to the independent variable, and then seeing what the result is for the dependent variable. So in this case, we would get 1 squared plus 5, because wherever I see that x, I'm going to replace it with 1. 1 squared is 1, plus 5 gives me 6. I'm going to have 2 squared plus 5. 2 squared is equal to 4, plus 5 gives me 9. And the last one, when I have an x value of 3, I get 3 squared plus 5, and I end up with 9 plus 5 gives me 14. So when I have an input of 1, I have an output of 6. An input of 2 gives me an output of 9. An input of 3 gives me an output of 14. And I'm choosing my language very carefully there. I'm actually adjusting language to steer you towards this idea of functions. So I've actually set that up. I've taken those values from my tables and I've reworded them using that language. The independent variables, another way we can think of independent variables is those are our inputs. Those are the values that we are putting into this relationship. And in particular, we're putting them into the x value, or the independent variable. And then this relationship performs some sort of calculation based on a set of rules. And then we get some sort of output, which is contained in this column. Same thing was true over here. As it turns out, our inputs, we just decided to use the exact same inputs, 1, 2, and 3. But because the rule of the relationship was different, the output turned out to be different as well. So even though the inputs were the same, a different set of rules can result in a different set of outputs. And we put all of this together in the context of functions by talking about them as if they are machines. And this is just an analogy, but it's something we can get our mind wrapped around. The idea of a mathematical machine. It's the idea that we have this mathematical machine that's got some rules that govern it. We take the independent variable, this is where the math part comes in, usually our x variable, but in general our independent variable, gets fed into the machine. The rules are going to take that independent variable and they're going to manipulate it somehow. And the manipulation could be something very simple and very obvious, or the manipulation could be something maybe so sophisticated that with our current level of mathematical knowledge, we're not really sure what's going on there. But then some sort of output will come out the other side. So that's a way of thinking about this thing that we're going to be focusing on so much, this idea of a function. A function is a machine that contains a set of rules. So this rule, that's your function. And more practically, in terms of math that you should be able to relate to quite easily, I could have this rule. I'm going to take whatever my input is, which is my independent variable x. I'm going to square that value, and I'm going to add 5 to the result. So if I were to feed the number 3 into this machine, which we already did in our table of values, 3 squared is equal to 9. Add 5 to 9, you end up with 14 as the result. That's our output, and our output is referred to as the dependent variable. If we don't have another label that we could or should use for that variable, we use the variable y. To go along with this kind of conceptual difference, there's also a notation difference, and the notation difference is pretty minor. We started with an equation that looked like this: y equals 3x minus, not minus 3, pardon me, 3x minus 2. And as you can see, I haven't made a change to the stuff on the right. The stuff on the right is the set of rules that define the relation. On the left, I'm just changing the notation a bit. And what that notation does, at first, you might look at this and say, well, all you've done is make my life more difficult because you've changed the notation, and the new notation is actually bulkier than the original. And that's true until you start working with it. Once you start working with it, this notation is actually a little bit more streamlined. Now, let's read this. This is saying the f is the machine itself. Now, you can call this anything you want to, but traditionally, we certainly use f for the word function, and then the next most common would be g and h. So the most common functions you'll see written are going to be f and g and h, but you will see some other ones as well. Then it's saying, and this is the part that students who are new to this concept, this is the part that they trip over. We are used to a set of round brackets like this representing multiplication, but they do not represent multiplication in this case. These round brackets are the input to the function. That's what they represent. So those round brackets represent the opening where you're going to drop the input into your function. And that's a hard one for people to get used to from the beginning. It's an understandable thing, but you need to get your mind wrapped around the idea that round brackets don't always mean multiplication. You're already familiar with that idea when we talk about a point. When we talk about a point with an x-coordinate and a y-coordinate, you're probably sophisticated enough at this point that you don't think of that as the letter p multiplied by this x comma y. This p is a label, and the x comma y represents a set of Cartesian coordinates. This f is a label, it's the name of the machine, and these brackets represent the input. What is it you are feeding into the machine? And then on the right side, you've got the definition of the rule. So here we have a mathematical machine called f, which uses the independent variable x as its input, is going to modify that input in the following way. It's going to take that input, triple it or multiply it by 3, and then subtract 2 from the result. Now, operating with this, I mentioned that it looks a little bulkier this way, but then when you start working with it, it actually is a little bit more streamlined. So if I say something like this, if I have f with that input bracket of 0, and the way we would actually say this out loud is we would say that is f of 0. So the of is the part that implies that it's a function and we are describing the input of 0. So this is the function f with an input of 0. The way that we resolve this is we take a look at the definition, which is 3x minus 2, but wherever there was an x, just like we would have done with the equation y equals 3x minus 2, wherever there was an x, I'm going to replace it with a 0, and then I'm going to complete the operations as instructed. 3 times 0, of course, is 0, minus 2 just gives me negative 2. F of 3, on the other hand, is going to be 3 times 3 minus 2. Wherever there used to be an x, I'm going to pick out that x and I'm going to replace it with whatever my new input is. So f of 3 is 3 times 3 minus 2, which is 9 minus 2, which is 7. And f of negative 5 is 3 times negative 5 minus 2. That's going to be negative 15 minus 2, which is negative 17. Now, I didn't tell you to pause there to try those exercises on your own. Hopefully you did. For this next group, I want you to try the exact same thing. I've redefined the function. This is not the same function anymore. I've given it a new set of rules. And I've made the inputs a little trickier, not terribly. What we did before still applies. Wherever you see an x, you're going to replace it with whatever the new input is. So pause this, give this a try on your own. And then I'm going to go ahead and work through it. I'm going to probably need a little bit more room than I have here, so I might have to spread out. F of 2a, so the function using 2a as the input, is equal to negative 2. Now I had negative 2x squared, but instead of negative 2x squared, I'm going to replace that with 2a. So wherever there was an x, I'm going to replace it with 2a. And then I had plus 5 times x, but I'm not going to have an x anymore. I'm going to have 2a here. And then finally, minus 1 on the end. Negative 2, I'm not going to rush through this. 2a all squared is the same as 2a times 2a, which is the same as 4a squared. Positive 5 times 2a is plus 10a minus 1. And now I can simplify this. Negative 2 times positive 4a is negative 8a squared plus 10a minus 1. Let's take a look at b. That one is f of negative 3b. And once you start to get the hang of this, you realize that this stuff about function notation is not particularly difficult or sophisticated, but it is something you need to grow accustomed to. Negative 2 bracket, so I'm going to write out the whole thing. Negative 2 something squared plus 5 times something minus 1. But in this case, I'm replacing x with negative 3b and negative 3b. Notice that this one is being squared, whereas this one is just a linear term. So it's just to the power 1. Negative 2 times negative 3b all squared is 9b squared. Positive 5 times negative 3b, that's minus 15b minus 1. And negative 2 times positive 9 gives me negative 18b squared minus 15b minus 1. And finally, let's finish off with c. F of x plus 2. Now this is interesting because notice that I'm not actually changing the character that I'm using for the variable. But the procedure that I'm going to use here is exactly the same. So I'm going to write it out the same way, just so you get used to that idea. I used to have negative 2x squared, but now I'm just going to put a bracket there, plus 5 times x, but now I'm just going to put a bracket, minus 1. And where I had the x, I'm actually replacing x with itself plus 2. So inside this bracket goes x plus 2. Inside this bracket goes x plus 2. And now a little bit more work here just from an algebra perspective. What is x plus 2 all squared? If you remember your special patterns, that's a perfect square, which expands out to x squared plus 4x plus 4. Otherwise, you can do it the long way with FOIL, expanding out the brackets. Plus 5 times x. This one I can immediately just expand the bracket using the distributive property. So I end up with 5x plus 10 minus 1. Just simplifying this is going to take a little bit more time. So I'm going to have to multiply this 2 into that bracket using the distributive property. Negative 2x squared minus 8x minus 8 plus 5x, and then plus 10 minus 1, I might as well simplify that now, becomes plus 9. And then finally, I only have this single x squared term, so that just becomes negative 2x squared. Minus 8x plus 5x becomes minus 3x. And negative 8 plus 9 is just equal to positive 1 on the end. So f of x plus 2 ends up being this quadratic equation. And this is as simple as I can make it. I've fully simplified it. So what have we really done here? We've introduced this new notation. The old notation that we referred to, and we didn't really give it a name before because it was the only way that we knew to represent things. That's typically known as XY notation because it has both the X and the Y explicitly in the notation. Whereas our new notation, function notation, has the definition of the function, and you notice here that y has been replaced with f of x. And that's why sometimes you will see references to this, which is that y equals f of x. What that's really doing is it's just acknowledging what we can see here when we have both of the notations written next to each other. The y, the independent variable, the dependent variable, which is y, f of x has taken its place, or that's what it stands for. So when you put a number in here for x, you're calculating y. Now, let's finish up with our final example. I'm giving you a definition here. Here's my function. F of x is defined as 3 times x plus 2. And now I'm turning it around a little bit. Now I'm saying, well, I want you to solve f of x equals negative 4. But that is the same as, I'll put this in a different color, that is the same as solve y equals negative 4. There's no difference. And so what that means is wherever there's an f of x, which is here in our equation, I replace it with negative 4. And so this actually turns out to be algebraically very simple because I end up with f of x was negative 4, so I replace it. And so I end up with negative 4 equals 3x plus 2. I subtract 2 from both sides, I get negative 6 equals 3x. And I divide both sides by positive 3, and I end up with negative 2 is equal to x. And the reason why this makes sense is the definition of the word solve. Solve means find the value or values of x that make the equation true. So if I want the result or the output to be negative 4, what did I have to put as an input to make that output? So when I put in negative 2, I end up with negative 4. Another way of saying that would be f of negative 2 equals negative 4. If I use this as my input, this is going to be the resulting output if I follow the rules of the function. Now, what about this next one? Solve for f of 2a equals 14. A little bit more going on this one because I can't just replace f of x. I actually have to substitute that in. So I'm going to do this in 2 steps. Once you're comfortable enough, you'll go straight to 1 step on this one. But what is f of 2a? Well, f of 2a, I used to have 3x plus 2, so that's going to be 3 times something plus 2. But of course, I'm replacing x with 2a. And so I end up with 3 times 2a is 6a plus 2. So now I know what f of 2a is, but what do I want f of 2a to be? F of 2a is supposed to be 14, so I'm actually going to replace f of 2a, and that's my second step. I'm going to replace f of 2a with that 14. And now, just some rearranging, subtract 2 from both sides, I get 12 equals 6a. And then I divide both sides by 6, and I end up with 2 equals a, or a equals 2. And so again, the use of the word solve in this expression, or this equation, solve f of 2a equals 14, I'm trying to find the value or values of the variable, and in this case the variable has been changed to a, that make this equal to 14. And so it turns out if I set a equal to 2 and put it in place of this a, well of course 2 times 2 is 4, so that would be f of 4, and that would give me 14. So let me just finish off this note. I believe this is the last slide. So let's say f of 2 times a, and a is 2, so f of 2 times 2. That, of course, we can see that's the same as f of 4. But that in itself, the function has its own definition, which is 3x plus 2. So that's going to be 3 times 4 plus 2. And of course, 3 times 4 is 12, plus 2 is 14, which confirms that my answer above here was correct. Algebraically, everything I've done here so far is, I would argue, for the level of math that you're being asked to do. All the algebra we did here is trivial, but conceptually, there's a little bit that you can stumble over here, so it wouldn't be the worst idea to revisit some of these things. Now, we're going to be going over these concepts again and again throughout the course, so you are going to get plenty of practice on it. For now, I have a worksheet. It's posted on the web page, and they're pretty simple questions on that worksheet, so 1 to 14 from that, and then some stuff from our current homework, from our current textbook for you to work on there.